Hello everyone. Thank you for watching this video, and I apologize for posting this very late. I promised this video on Tuesday, I believe, and I haven't had time to prepare this video until now. And regardless of the time, I mean, if you can watch this video, it's gonna be helpful for you. If not, I might revisit a little bit. I might cover more about this topic in class, right, face to face. But just in case you have a spare time, please watch this video. I promise I'm gonna make it short, so you don't have to be in front of the computer for a long period of time. But uh, let me introduce this topic, and let's see if I can do a better job compared to the job that I did the last year explaining this topic, right? Um, I'm gonna focus more on this lecture on the topic related to moderation, right? And how are we able to test moderation using regression models? You could also do the same with ANOVA, to be honest. But regression for me is a better tool in my case, and I believe moderation is better if it is explained in the context of a linear regression model. Uh, but well, let's start. Um, as I mentioned multiple times in class, um, even though in stats, especially in psychology, at the undergraduate level, we always teach only linear effects, right? And why do we teach only linear effects? Well, because it's easy to teach linear effects, right? And we believe that if we add more information into the class, students might get confused. In my case, I don't think that is true. If I give you more information, I'm very sure that you can make better decisions in the future when you are doing research, or in the context of your program, right? In the context of the psychology program, you will have more tools to think about your hypothesis when you are doing research on your seminars, right? So I believe this could be helpful. Probably not now, but could be very useful in the seminars once you take more advanced classes, right? So, as I said, we always teach linearity, right? And all the models that we teach typically in a stats class for the undergraduate level is linear. But today, I want to mention that there are models where linearity is not assumed, right? And actually, a linear model could be wrong in many cases, right? Like, for example, in this case, look at this data, right? We have our predictor, right? It could be any x variable and any y variable. And look at the data, right? It has this beautiful concave function right here, right? But there is a problem, right? The problem is that this is the model that we are trying to feed in this model. This is the model that we believe is the good model for this data. But look at the observed data, right? Look at the collected data. It doesn't look like a good feed for a linear model, right? We cannot assume this is linear. I mean, look at how far are the data points from a linear regression model, right? So probably this type of model is not the best, right? But we could make the regression line more flexible. And how do we do that? Well, we do that by adding polynomials. Polynomials are, probably you remember this from algebra, right? Our polynomials could be are another term, right? Where you add a quadratic term or a cubic term or at any level, right? So by doing that, what you are doing, right? By doing that, what you are getting is a more flexible line. Look at this case, right? In this case, what is the difference? Well, the difference is that we added another term right here in the equation, right? Which is something that we call a quadratic effect or quadratic term, right? So in this case, by just squaring the x, our x in this case is our predictor variable, right? Our observed predictor variable. You could get this beautiful, beautiful line that now is actually close to the data, right? So we can do this. We can do this type of things. And you might be thinking, when do I know? When do I know it's a good time for adding a quadratic term, right? Well, there are many ways to know. First is theory, right? If you have any theory behind your data, and from previous studies, you can see that, you know what? Probably the best model for my data is not linear. It could be quadratic, right? So that could be an option. Also, when you are exploring the data, when you are feeding different models, you can also test if this term is actually meaningful or not for your data. Like, for example, when you compare models using the AIC that I taught before, right? The one that I showed you before. By comparing different models, you could actually know if this model is better than the other, right? So you could test if this model is actually better than this one, right? Well, in this case, we don't need a test. We already know visually that it is the best model, right? Because it's closer to the data. So in this case, we don't need any proof because this is simulated data. But in real life, we might need to test if a quadratic model is the best model for data, right? Also, um, regression models are very flexible in the sense that you could add interactions between variables. And I will explain you what I mean by interactions. But first, let's take a look at this graph. In this graph right here, right? And actually, I should make it larger or zoom in a little bit, probably like this. So in this graph, okay, let me just check here. Okay, perfect. Okay, cool. In this graph, we have two variables. We have our x variable and our y variable. So that means that we have a predictor, right? And we have an outcome. Our outcome is our letter y. But there is something interesting here. We also have a third variable right here. And it's actually pointing to the relationship between x and y. Why is that happening? Well, it's because this is something that we call moderation. Moderation happens when there is a third variable that modifies the relationship between x and y, right? Um, for example, um, the relationship between um, let me see, I could see a moderator of, for instance, the for example, the relationship between body fat and diabetes, right? And you might be thinking, what could be a third variable, right? And that one could be, for instance, genetics. There could be a third variable that, for example, you might have something called polymorphism or a variation in your genes, right? That might explain or might change the relationship between body fat and diabetes, right? There could be something. And that's something that we call For example, that's something that we call, oh, I forgot the name. I'm losing my mind. I will remember later during the video probably. But yeah, there could be something modifying this relationship, right? Now, oh, let me delete this. Let me just erase this part. Perfect. When you see this type of plot, we are talking about the word depends. So when you create hypotheses for your studies that says X, the relationship between X and Y depends on Z, you are talking about moderation, right? And actually the model looks like this. This is something that we call the analytical model, right? This is our conceptual model. And we have the analytical model right here. So the analytical model looks like this. In real life, in our equation, we are going to have a independent variable. We are going to have another term for our moderator. And look at that, a multiplication between our predictor and our moderator. So it will look something like this. Let me just delete this part. It will look like this. So we have one term right here for X, another term for Z. That means that we are going to have a slope for our predictor, one slope for the moderator, and one slope that is the result of the multiplication of our predictor by our moderator. So X by Z, right? Oh, sorry about that. It moved a lot. I don't know why I did that. Oh, Jesus Christ. Yeah, right here. Right? Let's see this with an example. Probably it will make more sense once we see an example. In this example, we are going to have three variables in this data set that you can actually open, right? You remember that everything can be opened in your computer. And in this case, opening the data from a repository, so you can copy this and just open this in your R session if you want to run this. So in this example, we have a data set that has a variable that measures stress. We have social support, and we have depression, right? And we have an interaction term that is the product of multiplying stress by social support, right? So in this example, I want to test if the relationship between stress and depression is moderated by social support. But first, I need to know if social support and stress are related to depression. And this is actually the model that I'm running, right? We have stress and we have social support, and our outcome is depression, right? As always in this class, we're going to talk about depression a little bit. Let's take a look at the numbers, right? Let's see the output right here. So it's telling me that social support is actually related to depression, right? And that relationship is not explained by chance. The same happens with stress. It's telling me that the relationship between stress and depression is not explained by chance, all right? And it makes sense, right? Now, let's take a look at the slopes right here. So the slope for social support is negative. So that means that it looks like this. Let me just draw a picture here. We have social support here. We have depression right here. And what we have is a negative relationship. That means that when you are high on social support, let's imagine you move right, on this axis towards the right, you have a higher score, right, in social support. So if you are high in social support, you are low on depression, right? That makes sense, right? So it's telling me that when social support increases for one, well, actually the right interpretation is for 1 unit increase in social support, depression decreases 0.43 units, right? That's what it's saying. So it's decreasing, right? And as I said, it makes sense, right? If you have a social network, if you have a social support network that can help you to overcome your feelings, that will help you to make you feel better and be with you when you are depressed, of course, your depression will decrease, right? Your symptoms of depression will decrease. The relationship between stress and depression is positive, and that actually makes sense, right? Let me draw another one. Let me go here. So when we are talking about stress, right? Let's go here. And we have depression here. The relationship is positive. That means that when people are more stressed, they have more depression. That also makes sense, right? If you are very stressed, your relationship between stress and depression gets stronger, right? So it kind of reflects what we already know, right, about psychopathology. Oh, and let me give you the interpretation. This means that for 1 unit increase in stress, depression increases 0.13 units, right? That's what it means. I actually don't remember if this data is standardized, to be honest. I don't remember. Let me double check that very quickly. Let me just copy this into RStudio. 1 second here. Because I don't remember if I standardized the distribution, and we will find out. Let me just open the data 1 second and remind me later. And oh, that's not what I wanted. I wanted to copy the whole thing. Cool. Nice, that's better. So let me open this very quickly. And then we double check the distribution of these variables. Let me see. No, they are not. Yes, they are not in a standardized metric. And that's okay. That's totally fine. Right? Yes. Yeah, probably this one, social support C probably is. But yeah, these ones are not. So yeah, that's fine. That's fine. And actually, it's good to see the values that we have in the data set. So we have a stress, right? The minimum value in this data is 4, and the maximum value is 92 in social support. The minimum value in this data is 8, right? And the maximum value is a score of 28. I don't remember what is the maximum and minimum of these scales because, to be honest, I didn't do this study, so I don't know what instruments they were using. I don't know what is the real minimum and the real maximum, but at least we can have a picture of how the data looks like by looking at these numbers, right? All right. Let's go back to the example. So this is the equation that I have in mind, but I also have a hypothesis. I believe that social support could be a moderator, right? Our z value, our z variable, sorry, and stress is the predictor, right? So I believe that there is an interaction between x and z. In this case, I have evidence and let's imagine that I have evidence for that, right? From previous research projects. that it is possible to think that stress and social support are actually interacting. Interaction means moderation, and moderation is related to the word depends, right? So in this case, what I'm saying in this equation is that the relationship between stress and depression depends on social support. That's what I'm saying, right? And actually, I should write it down. And let me see what happens when I copy this. Oh, probably cannot do that. So let me just go here 1 second. And let me try something. That's nice. Yeah, it stays like a picture. That's interesting. Okay, so good. What I'm saying is that the relationship between stress and depression depends on social support. When I have this type of statement as a hypothesis, we need to fit a model like this one. So what we are going to do is just multiply stress by social support. And that's our moderation term or our depends term, right? So it's an interaction. That's how we make this more operative in terms of statistics. Now, let's take a look at the model when I add my interaction term or interaction effect, right? So look at this. I have an interaction here, and this is the slope of the interaction. The slope by itself is not very meaningful, and sometimes it's hard to interpret depending on the scale, right? We are not gonna interpret this number. We're gonna do other steps. We're gonna take other steps in order to understand that number. But in this table, the most important part is this p-value right here. This p-value is telling us that this interaction is not explained by chance. Look at the p-value. It's way less than 0.05, right? So this one is, this number right here is less than 0.05, right? So that's good. And my hypothesis is true. Well, we are not saying true or false, but at least I have evidence that I could hold my hypothesis. Yes, there is an interaction that is not explained by chance between social support and stress, right? At least in this data set, right? If you find that interaction term is not explained by chance, you cannot interpret the individual terms because they are modified or depend on C. Let me explain you what I tried to say here. Ah, look at that. You can download the data from here too, by the way. What I'm trying to say here is that when you have a interaction that is not explained by chance, you cannot interpret these terms anymore, right? This is something that we call a higher order term or higher level term. So when your higher level term is not explained by chance, these two terms, these two slopes are not meaningful anymore. You have to interpret this interaction right here. That's what I'm saying here. And that's something that we are going to do in the next slides. So our model looks like this. We have stress and depression, right? Stress is our X variable, is our predictor, and Y, in this case, is depression, right? And our moderator is social support that we're going to call Z, right? Our Z variable. So now it's more meaningful, I believe, for you, right? It makes sense, right? So now that we know that there's interaction, we need to analyze this interaction. what we are going to do, let me just show you here. Oh, let me just probably go here, right here. What we're going to do is to analyze how is the relationship at different levels of social support. So it's another conditional statement. If you see the word depends or interaction, that means that we have a dependency. We are saying that the relationship between stress and depression depends on social support. And we can analyze that relationship at different levels of social support. And that's actually what is behind the interaction hypothesis. The hypothesis about interactions is more related to levels of your moderator. So we need to analyze the relationship between depression and stress at each level of social support. But of course, it's hard to do that. So what we do is to estimate the effect, right? How is the regression line when people are high on social support? And in order to do that, we add one standard deviation to the mean of social support, right? And we also analyze how the relationship between stress and depression looks like when people have an average score on social support. And also we are able to analyze when people have a lower score in social support. What happens with their relationship when their social support is less, right? So let's take a look at this plot. As you can see here, oh, I wonder what's this. Okay, as you can see here, when people have a low score, and that is this red line, when people have a low score in social support, that means that they don't have a very good social support network, right? When they don't have that, the relationship with stress and depression is steeper. Look at that, and positive, right? When people have an average score on social support, or their score is close to the mean of social support, the relationship between stress and depression actually is less steep, right? It's less steeper. So look at that. The line or the slope is not as pronounced as this one, right? Look at the line. It goes up faster. This one goes up slower, if you can say that. And now take a look at what happens when people are when people are high on social support, right? That means this blue line right here. The line, look at the slope, right? Is kind of turning a little bit flat. So that means that the relationship between social support and depression is stronger. Sorry, the relation between stress and depression is stronger when people have a low score on social support, which is interesting, right? So that means when people don't have a network, don't have friends, don't have family to support them, to make them feel better, right? The relationship between stress and depression gets way stronger. And that also makes sense, right? Now, let me tell you something about a concept called simple slopes. Um, Given that we cannot use calculus here, we cannot estimate the simple slopes by hand, but we can estimate this concept in R using a package, right, with computers. But let me see if I can make a good job on this. If I can do a good job on this. This is our model, right? This is the model that I just estimated. And I plotted different lines, right, at different levels of our moderator. That's what I did, right? Those lines right here, well, let me just come back to the previous slide. These lines here are something that we call simple slopes. I know it's kind of a it's not very descriptive, right? It's not very informative to say simple slopes. But they are called simple slopes because we are kind of decomposing the main slope into different slopes. We are trying to find different functions at different levels of our moderator. That's what we are doing. So we are estimating multiple functions or partial functions, right? Like I do here. So we can take this mathematical formulation, right, and change it and rearrange all the terms in a way that it looks like this. So by doing this, we can get a function for z, right? And remember, z is our moderator. So we can get a function for the relationship of that inner relationship of z, right? Well, or the relationship that corresponds of with z, right? Given the other terms. So once you get this function, and let me see if I have another thing here. Yes, perfect. Let me just delete this part. Once you get this function, you are able to plug in values here and get different linear models or linear estimations, right? Because you have this function right here. Of course, you have to use calculus, and then the final product is going to be like that. We are not going to do calculus, but believe me, the final product is going to be like this. So this function will help us to plug in values here. So what's going to happen? Well, we can create different lines at different levels of z. That means at different levels of our moderator. So for example, we can have, and let me just do it here. And actually, no, let's do it here. Let me just come back to, no, don't do that. Let me come back to my word processor here. So we can have a new line, right? And actually, let me copy and paste this. Probably can't do that. Oh, look at that. That's nice. Oh, and I can change many things. Oh, perfect. All right. So let me just copy this. Right. And instead, and let's move this part here. We can actually have function for the mean of z, right? Let's call this mean, right? And in here, we are going to get a new variable where we calculate the distance from the mean, right? So it's like having a variable, right, that is close to the mean, right? So now we are able to estimate a regression model. Well, yes, it is actually a regression model, or regression line, right, at the mean level on your moderator. And we can also do the same. Oh, it's doing a mess. I thought it would be better. And we can also do the same for people who are, for example, located at 1 standard deviation below the mean, right? That's what we call observations that are 1 standard deviation up, 1 standard deviation below the mean. And we can also estimate an slope or another function for the individuals who are located above the mean or 1 standard deviation above the mean, right? Let's do it like this. So these functions that I just mentioned here, right? These three functions will help us to create three different lines. So we will have a line or a regression line when people are high on social support. Let's call it SOC. We will have another line when people are low on social support. And we will have another line. Oh, this looks ugly. Let's see if I can make it better. Right here, probably. And another line when people are close to the mean on social support, right? So now we are kind of decomposing the relationship between stress and depression by different levels of social support. Let's see how you can do this by hand. And actually, I did it here, I guess. Oh, I didn't add the code, probably. I probably didn't want you to know the code by hand. But well, and oh yeah, it's right here. Sorry about that. I just found it. Here it is. So how do you do it by hand? Well, what you have to do is to estimate the distance of every individual from the mean, right? That's going to be the variable that you will add into the regression model in order to get the slope for the scores when the score is close to the mean, right? Or far from the mean. So in other words, what you are doing is mean centering your predictor, right? This is like mean centering. So what you're estimating is how far or how close is each individual from the mean. You will create another variable where you estimate the distance of people, right? Each individual, and how far they are from one standard deviation above the mean, right here. And in the other, you will create another column that estimates the distance, right, of each individual from the value that represents one standard deviation below the mean, right? And you can see the code right here. This is from tidyverse. We always use tidyverse in this class. And you can see how I did it, right? What I did was to take the column in the dataset and just subtract that, right, from one standard deviation, the number that measures one standard deviation above the mean, right? And if you're curious about it, I can show you the numbers. Well, actually, there are plots here. They're better. So, and let me just remove this. You don't need this piece of code. The only thing you need is this. So once I create a column for the mean level of social support, the distribution looks like this, right? And people who are close to zero, right? They're closer to the mean, right? So now is mean centering. In this case, the mean, well, the mean is going to be zero again, it's the same. But these are the people who are high on social support, right? I mean, the scores when they're high on social support. And of course, the zero, look at that, it moves to the right, right? Why? Because now it's representing how far are people from one standard deviation above the mean, right? That means higher scores. And now the zero, in this case, in social low, is moved to the left. Why? Because here we are capturing how far are people from one standard deviation below the mean, right? So now we have a variable. Well, we have three new variables, three new columns. Social mean represents when people are close to the mean. Social high represents when people are high on social support. And social low represents when people are low on social support, right? And given that we computed this these, given that we computed these new variables, these new columns in the data set, now we can get a number. Look at that, and a slope for each level. So in here, I'm doing an interaction of stress by my new column. In this case, this column is the column that represents the scores, or how far are the scores from the mean, right? And that will give me a slope. I will do the same in order to get a simple slope. That's how we call this a simple slope. Instead of doing this by calculus, we can do it by hand, right? Sorry, we can do it by, oh, y looks very similar in all of them. Ah, because the difference is very similar. Oh, look at that. There's something wrong in this code. I'm printing the same one all over again, I guess. Social law. Oh, what is going on here? Oh, it's because it's very similar. Look at that. Oh, yeah. The difference between them is very tiny. Look at the slope. That's interesting. Yeah, it looks very similar to this one. But the intercept is different, yeah. Stress social high. Yeah, well, that's what it is. So I have a slope for each of the levels, right? So now we have an interaction by the scores when they are low, middle, and high, right? That's what we are doing. And look at the p-values. They are not explained by chance. Yeah, I wonder why they are so similar. Let me see if there's a mistake. This is the mean. This is when people are high, the scores are high. Let me check. That's a good thing about having a language, a scripting language with code. You can always check what you did. And that's nice. Now everything looks fine here. Let me check if there's a mistake in the estimation of the columns right here. No, it is fine. Plus, plus 1 standard deviation and minus. Yeah, no, everything looks fine. Everything looks fine. It's just the slopes are very similar. I wonder why. Well, yeah, yeah, perfect. No, it's fine. It is fine. It is perfect. So in here, let's pay also attention to this slope right here. So this is the slope that we call the simple slope. Now, by doing this mathematical trick, this becomes the estimation, the partial estimation of every simple slope. So that's nice, right? So now we have a partial, we have a simple slope for stress. When people are, well, when the scores are close or far from the mean, or when the scores are far or close to be on the high level of social support. And this is the simple slope, right? For people when they are low on social support. I was just checking this number here. That's what I was checking because I saw that it's very similar, right? And the modifier is very similar, 0.002. It's probably because, well, that's how it is. I was just checking the number. The numbers were fine, and yeah, they do make sense. Yeah, everything looks fine. With the calculation in my head, it should be fine. Yes. And look at this. Look at something that is happening here, actually. The simple slope, that means the relationship between stress and depression, is actually explained by chance when people are high on social support, right? That's something very interesting. So what is the interpretation? The effect of stress on depression is stronger when participants have a low level of social support, right? We already know that. We saw a plot, right? The effect of stress on depression gets weaker when participants are close to the mean of social support. And the effect of stress on depression gets much weaker when participants have a higher score in social support. And actually, this simple slope is explained by chance, right? Because the p-value is a little bit larger to 0.05. Now, you might be thinking, well, can I test the relationship between stress and depression at each level of social support? Well, the answer is yes, you can, right? So we can do something called the Johnson-Neyman interval, or Johnson-Neyman technique. That's also called like that. Actually, I'm calling it like that here. So by running this code using the package, oh, I need to delete this part to pay attention to this note right here. If you use the package interactions and run this function, that's the only thing you need, right? You can get this beautiful plot. And it's beautiful because it's a beautiful technique where you can see when the relationship between social support and depression, the relationship between stress and depression is explained by chance at different levels of social support. So this blue line right here, let me see if I can do, yes. This part that is blue represents the region when the relationship between stress and depression is not explained by chance. So when social support approaches up to, what is this? Yes, 30. Oh, that's weird. Social support outside the interval 23.12. Oh, yes, 28 and 50 right here. So when people are approaching up to 27, something like that, is social support, right? The relationship between stress and depression is not explained by chance. But when social support, when people have a larger score in social support, and this is something very interesting, when people have a very high score in social support, above 28, actually, the relationship is weaker, right? And is explained by chance. So what is the message here? It's telling us that what we already know. When people have a very good social network, when they have a good interaction with family and friends, right? Their levels of stress, of course, decrease, right? And therefore, the relationship between stress and depression gets weaker, right? Up to the point that it's almost flat. And actually, we saw it in our plot before. Let me just show you here. This test is telling us what we saw here, right? Look at the blue line. The blue line represents the relationship between stress and depression when people have a high score in social support. And when that happens, look at the line, right? The tendency is to become flatter. That means there is no relationship, right? So we just found out that the relationship between stress and depression is stronger. In fact, when people have a lower score in social support, that means that they are lonely, right? They don't have friends, they don't have family to support them. So when that happens, stress goes up and depression goes up. But when they have a good social support network, the relationship of stress, the levels of stress actually decrease, and the levels of depression also decrease, right? So that's what we know, right? And that's good, right? That's something that we already know from the literature, right? Also, let me show you something else before I finish this lecture. We are almost done. I might explain more in class, so watch out. Oh, you can also ask me as many questions as you need in class or by email. But let me show you something here. This function will also give you the simple slopes estimation. These are the numbers that we got before by hand, but now it displays automatically. So all the things that I did to create new columns in the data set and everything is not necessary. I show you how you can do it by hand, quote unquote. But you can just run a simple function in R, and it will give you the estimation of the simple slopes, right? And look at how the relationship between depression and stress and depression decreases when you are high on social support, right? When you have a high score in social support, that relationship gets weaker, right? It is stronger when you have a low level of social support, right? You can see the slope is 0.22 when you have a low level of social support. Then the simple slope decreases at 0.13, and then it decreases at 0.06, very close to zero, right? So, that's nice, right? Now, you might be thinking, how can I use this? Well, you will use it in the seminars. If you take the seminar with me, you will use this. You will have probably hypotheses that are related to interactions or what we call moderation, right? Why? Because it's funnier. It's better when you test these type of things because nature is complicated. And if we stick only with simple examples, people will not do very fun, like funnier, I would say. People wouldn't do funnier in models that are closer to the data generating process, right? Because that's our main goal. Always remember that. We need to find a model that is closer to the data generating process. And probably a model with a moderation could be the best model that is closer to the data generating process, right? And finally, I just want to give credit to my friends Kyle Lang and Mauricio Garnier Villarreal, very good friends, and I took some of his ideas and some materials that I had from them. So I just want to give credit to these amazing people who I have met in my life, and they have been amazing how can I say, mentors in my life. So thanks to them for this lecture. I took some parts from what I know from them, and I just want to give credit to these people. Well, thank you. Thank you so much for watching this video, and see you in class the next week, hopefully, if everything goes fine. Thank you so much, and take care.